Yes, can you start the recording? Good morning, everybody, and welcome to the High Energy Density Science Center Seminar Series. We've had a bit of an annual tradition now that each of our of the HED Center's postdoctoral fellows get to give a talk so they can introduce themselves to the community here. And so I hope everybody's able to give a warm welcome to our current postdoctoral fellow, Elizabeth Simpson Grace. Liz began her role as the HED Center Fellow this past January, so she's brand new. And she received her PhD in physics from the Georgia Institute of Technology last year, co-supervised by her academic advisor, Rick Trevino, and her technical mentor, Tammy Ma. She's an avid hiker, having recently completed the Appalachian Trail. And please be aware this talk is being recorded, so if you're uncomfortable with that, please log off. Also, if you're online and you have any questions, please put them in the chat field and I will read them after Liz's talk. Otherwise, please take it away.
Hi, so as Paul said, I'm the current HED Center Fellow, and today I'll be talking to you about my thesis work. The title of my talk is On-shot spatiotemporal laser wavefront characterization via wavelength-multiplexed holography for precision control of high-intensity laser plasma interactions. So on the right, I've plotted a measured laser pulse that has astigmatism and chirp. So here, the spectral components of the laser pulse have been mapped to RGB with longer wavelengths in red and shorter wavelengths in blue. Characterization of the complete four-dimensional electric field, EXYZT, of the short pulse lasers on a single shot is difficult, and so most laser plasma experiments and simulations rely on Gaussian assumptions of the laser's spatial and temporal shape. But to truly understand the laser plasma interaction physics and to have predictive capability, we need complete pulse measurements. This work demonstrates the high-intensity single-shot measurements of EXYZT and investigates the relationship between laser spatial and temporal structuring and the physics effects downstream. So this talk covers advances in high-precision laser electric field measurements and control. The first section of my talk will cover high-intensity on-shot laser electric field measurements. And I hope that at the end of that section, you'll understand this movie, what it's plotting, and why it's important. The second section of my talk covers temporal structuring for optimization of laser-driven particle sources. And the third part of my talk covers spatiotemporal structuring of laser intensity and phase to generate optical vortices. So I'd like to thank my collaborators at UCSD, Georgia Tech, CSU, and of course the group at Livermore. So from proton radiography, neutron radiography, and X-ray radiography to electron and ion acceleration, laboratory astrophysics, medical radiotherapy, and stress testing, high-intensity laser plasmas form the basis for many interdisciplinary applications. So here I have a plot of the peak power of laser systems as a function of the year that they were built. Around the world, investment in laser technology has produced increased peak powers, and the takeaway here is that accurate laser characterization is crucial for every single one of these high-power laser systems, but remains a gap. Livermore is the leader in developing high-peak power lasers, and characterizations of these lasers is crucial for the applications in HED science. Research with short pulse lasers is a large part of the work here at the lab, from developing predictive capability at ARC to secondary source applications. So I'm beginning the first section of my talk, which covers high-intensity on-shot laser electric field measurement. So to understand why we want to do this, every single ultrafast laser pulse can exhibit complex spatiotemporal couplings, which are usually not diagnosed. So the first coupling that I'll go about describing is in the space-time domain, which can happen. This coupling can happen, for example, if you have this pulse coming in from the left onto a tilted slab. The bottom of the pulse can propagate directly through while the top resonates, and this produces a coupling between space and time, which is called pulse front tilt. The simplest electric field expression for this pulse is a Gaussian in space, a Gaussian in time, and a linear cross term between xt, which is modified by the coefficient qxt. When the real part of qxt is non-zero, then your pulse acquires pulse front tilt. The next distortion or coupling that I'll talk about is in the spatial frequency, so space frequency domain. So for instance, if you have a pulse propagating through two prisms, it could emerge with this dependence between the spatial position and frequency, which is known as spatial chirp. The simplest laser electric field expression for this pulse has a Gaussian in space, a Gaussian in frequency, and a linear cross term between x and omega, which is modified by Rx omega. When Rx omega is non-zero, then the pulse has spatial chirp. When the real part of Rx omega is non-zero, then your pulse has spatial chirp. This third distortion is probably the most well popularized. This is called angular dispersion. So this is when you have a dependence between the angle of the laser pulse and the frequency. Again, we have our Gaussian in frequency, but now we're moving into the k omega domain, so the spatial frequency domain. So we've got a Gaussian in k space, a Gaussian in frequency, and the linear coupling between k and omega, which is modified by sk omega. And when the real part of sk omega is non-zero, then your pulse has angular dispersion. This fourth effect is described by analogy to the time versus angle variation of a lighthouse. So in this distortion, you have your pulse intensity front actually rotating as a function of time. And that's called the ultrafast lighthouse effect, or sometimes time versus angle, or TVA. So when you have this effect, the simplest electric field expression is a Gaussian in k space, a Gaussian in time, and the real part of the coefficient describing that linear coupling between k and t is non-zero. So these four effects occur in the intensity distribution of the laser pulse, but you can also have couplings in the wavefront of the laser pulse, and that occurs when the imaginary part of that coupling coefficient is non-zero. So now we're back into the x omega domain. So spatial chirp also exists in this domain. So we have the exact same electric field expression for a Gaussian pulse with a linear coupling, except now the imaginary part of that coefficient Rx omega is non-zero. And what this produces is a dispersion in the wavefront tilt. So like at redder frequencies, you have one tilt, and at greener frequencies, you have a different tilt. And you might have this motion, if you're looking at the different frequency components, you'll have this dispersion in the tilt of the wavefront. So that's again in your x omega domain. If you move into your xt domain, now you can look at the imaginary component of qxt. You have your same electric field expression as for pulse front tilt. You have your same linear coupling modified by qxt, but now the imaginary part of that coupling is non-zero. And so what that produces is a change in the wavefront tilt as a function of time, or in other words, a wavefront rotation. So these are not, this isn't an exhaustive list of all of the spatial temporal couplings, but this should get you started for the rest of this talk. So here's a measured laser pulse measured at the Georgia Tech oscillator. It's coming towards you out of the screen. X and Y are the transverse positions. And you have the frequency, the spectral components of the laser are mapped to RGB. So the colors in the laser pulse represent the spectral components. And this pulse has temporal chirp, which can be seen as the pulse starts red and ends blue. Spatial chirp here, as you see a rainbow across the laser pulse. And pulse front tilt as the pulse starts off on the right and ends on the left. Spatiotemporal distortions can be very detrimental to focal spot intensity. So here we have the ultrafast lighthouse effect. So you can see that these pulse fronts, the angle of the pulse front is changing as a function of time. So that's your time versus angle. And at the focal spot, so above is the measured and below is the simulated. So you can see that at the focal spot, you've got a chromatic smear, both in the measured and the simulated data. And basically that produces a diminished focal spot intensity. So you could have all of the colors at the same location. This is another example of some distortions that can occur. This is a focusing pulse with with chirp from like material dispersion in the lens. So the red portions of the pulse are arriving before the green and the blue. You can also see that there's more red on the outside and more blue towards the inside, which is your chromatic aberration, your spherical aberration before the focal spot. And there's even like some diffraction going on, producing this little spot in the middle of the pulse that's in front of the rest of the pulse. So basically, you can have a lot of different effects that can damage or change your focal spot intensity. So existing pulse measurement techniques generally only measure pulses in time or frequency. So for example, frequency-resolved optical gating, or FROG, and its cousin Grenouille, capture the intensity and phase of the laser pulse in time, but averaged over space. So to note, you can get like some first-order spatiotemporal distortions from FROG and Grenouille. You can get the pulse front tilt and the spatial chirp only along the X direction, but in order to measure the complete field, you would need a more complicated and more robust device. So it's fine to measure just the temporal and the spectral components separately, so long as you have a separable electric field, but that is not generally the case. So just writing out the full dependencies of the laser pulse, so we have those same equations for the electric field in the temporal electric field, the spectral electric field, and you have that Fourier relationship between omega and t. And to measure these spatial and temporally dependent fields, you need a complete spatiotemporal pulse measurement device. Complete meaning that it's not just measuring the first order spatiotemporal distortions, but that it's measuring higher order spatial-temporal distortions as well. And also due to low repetition rates in high power systems and instabilities in any repetition rate laser system, we also require single shot measurement. Striped fish solves this problem by taking single shot complete spatial temporal pulse measurements. So the basic principle of striped fish is holography. So here I have on the right a spatially uniform monochromatic reference beam coming down and an unknown beam reflecting off of an object, and they interfere on the camera, producing this speckle pattern. You measure the integrated intensity IXY of the sum of the known and the unknown monochromatic beams, and then you extract the unknown monochromatic field EXY from the cross term. So here I have the basic equation of holography, which is basically that you have your DC term, which is your intensity of the reference, the intensity of the unknown, and then you also have your rapidly oscillating term, which depends upon the relative spatial phase of the known and the unknown pulses. So holography can provide the wavefront of the laser pulse. So how do we apply it in striped fish? So striped fish is an acronym for spatially and temporally resolved intensity and phase evaluation device, full information from a single hologram. And the way that it works is that you have this reference pulse and the unknown pulse coming in at an angle incident onto the slightly rotated two-dimensional diffractive optical element. So that's rotated actually around the propagation direction. And you have the two coming in at an angle because eventually you're going to produce spatial fringes on the camera, so you need them to have a relative angle. And then after they are passed through the DOE, the diffractive optical element, that produces basically this array of beam pairs all carrying a different angle. And that's then used at the interference bandpass filter. So you have basically an array of copies from this really coarse diffraction grating that's not very, the purpose is not to be dispersive. It's to generate multiple copies of the beam pairs at different angles. Then you're incident onto the interference bandpass filter, and you've got basically the copies with their different angles. Because they each have a different angle of incidence, they each have a different transmitted center frequency, because it's an interference bandpass filter, so it sees a different thickness depending on the different angle of incidence. And so then on the opposite side of that bandpass filter is basically a spectrally resolved array of holograms or of these interference fringes. So each one of them has a specific frequency representing a frequency component of the pulse. So you have this array of spectrally resolved holograms that you can use to get the wavefront at each frequency present in the laser pulse. So here's a theoretical striped fish trace for a single pulse where false color is indicating frequency. So basically this is for some undistorted pulse. You can see that you have your interference fringes at each of the different frequencies present in the pulse. The striped fish retrieval algorithm gives you the complete pulse spatiospectral field. So here is on the top this false color sample trace. You crop out one of your holograms and you take it back into the KX-KY domain, where you select one of those AC terms, which you then Fourier transform. You take the inverse fast Fourier transform back into the XY domain, and then you have the intensity and phase versus X, Y, and frequency. You can then take the inverse fast Fourier transform from frequency to time to get your electric field as a function of X, Y, and T. And then to get your EXYZT, you can use angular spectrum diffraction integrals to propagate the pulse. Striped fish can measure laser pulses from around femtoseconds to 10 picoseconds in duration. The temporal resolution is limited by the frequency separation of the holograms. The spatial resolution and range are limited by the camera, and the temporal range is limited by the spectral resolution of the bandpass filter. You can increase the temporal range significantly to use by using multiple delays, but then you would no longer have a single shot device. So you can actually see a lot directly from the striped fish trace. For example, if you have an undistorted pulse coming in and you take 3 sample holograms at 785 nanometers, 800 nanometers, and 815 nanometers, for an undistorted pulse, these 3 holograms should be basically identical. There should be no difference for an undistorted pulse. So the striped fish trace exists natively in the spatial spectral domain, the X omega domain. So everything that you read off of the trace is going to also come from that domain. So if you recall, that's your spatial chirp and your wavefront tilt dispersion. So spatial chirp is, again, that intensity effect. So it manifests in the intensity of the laser pulse. So you have the real part of this coupling term is non-zero. And what that produces is a motion of the intensity distribution of the unknown pulse with respect to the reference pulse. So here I've simulated spatial chirp in X and Y. And on the trace, what that looks like is as you are changing the frequency, the position of your unknown pulse is moving or sweeping across the reference pulse location. So then that wavefront tilt dispersion, which is that wavefront effect that I was talking about in the spatial spectral domain, that'll produce a change in the interference fringes, which is actually different depending on whether you have wavefront tilt dispersion in X or in Y, because we've chosen the angle to be, the crossing angle to be in Y, because we've chosen our spectral dispersion to be in X, which is just that angle of the bandpass filter. So we have in Y, for example, since your wavefront tilt is changing with your frequency, that basically manifests as a change in the crossing angle for the fringes, or which changes the fringe spacing. So in Y, basically, since you're already crossing in that direction, this basically looks like the spacing changing as a function of frequency. In X, because there was no difference in the crossing angle in X, this becomes a rotation of the fringes. So here I've simulated wavefront tilt dispersion in both X and Y, which means we have both the rotation of the fringes and also the spacing of the fringes changing with frequency. And of course, you can have both at the same time. And then what you'll see is a motion of the spatial profile and a rotation of the fringes. And you can even have both of those effects on a pulse that you measure. So reading these changes directly from the trace results in a rapid algorithm for high repetition rate feedback. These plots show the retrieval performance for different coupling strengths as described by the normalized scalar rho, which gives you a scalar value for the spatiotemporal coupling. So on the left, I've plotted the center shift, which is the spatial chirp in millimeters as a function of frequency. And on the right, I have the fringe spacing, which is your wavefront tilt dispersion in Y as a function of frequency. And you can just see that for different values of rho, the measured and the simulated values match really well. So you can basically get the same first order information as the complete striped fish retrieval, which is, a complex 4-dimensional retrieval. And this simpler first order retrieval provides the same first order information with less than 1% error, even for highly distorted pulses. And also, due to the interrelation of spatiotemporal couplings for collimated beams, you're not limited to just knowledge of the spatial chirp and the wavefront tilt dispersion. You can actually get to first order the rest of the spatiotemporal couplings present in the laser pulse through those relationships. And so this is basically like if you had a laser system and you want to know like what are the first order effects that I can immediately change the alignment and fix those problems, this would give you that answer. So the first on-shot full power spatiotemporal measurement was taken at the Jupiter Laser Facility's Comet laser here at the lab, which I'm sure y'all are familiar with. 28 shots were taken over one day. This is the setup that I used on the left. Comet, that's the compact multi-pulse terawatt laser. It's got a rep rate of like 1 shot every 5 minutes. The max energy on target when it's is about 10 joules and the short pulse length is 1 picosecond. This work was done in the calibration stage right after we moved the laser from the right hand side of the hall to the left hand side of the hall. So just there have been a lot of improvements made to Comet since these measurements were taken. But this is the raw single pulse data of Comet, the Comet short pulse, the maximum available intensity at that time, which was 0.3 joules. On the left, I have the calibration trace, which is my spatially smoothed reference pulse. And on the right, I have the data shot, which has the reference pulse and the signal pulse overlapping. So striped fish provides the spatial spectral intensity and phase, and it does so directly. So on the top, we've got our intensity as a function of frequency. You can see that at different wavelengths, you have a different spatial profile, and that's your spatial chirp. If you can see on the bottom that the phase you have different basically fringe spacings and different rotations as a function of wavelength, and that's your wavelength, your wavefront tilt dispersion. So you can see basically directly from this information, you already have those two couplings. The retrieved movie shows spatiotemporal complexity as we would expect from the trace. So this pulse is coming towards you. The X and Y are the transverse dimensions of the spatial profile. The spectral components of the laser pulse have been mapped to RGB. And at Comet, you've got like a 4 nanometer spectrum. So you can see temporal chirp as the pulse starts off red and ends blue. Again, you can see your pulse front tilt as the pulse is beginning on the lower left corner and sweeping up to the upper right corner. And around here, you can see that spatial chirp as well. So that was for a single shot, but I was also curious to see like what are the trends that are emerging, like what are the systematic effects that I'm seeing at Comet. So here I have the integrated intensity over xt for pulse front tilt, which gives you the pulse front tilt. So basically the linear pulse front tilt is the angle that this intensity pattern has with respect to that normal line. So when there's an angle there, that's the angle of your pulse front tilt. And similarly, if you look at the intensity integrated over all shots in the x omega domain, you have this smaller angle where you have the angle between the ix omega integrated intensity and what would be zero distortion, which would be like a vertical line. So that's your spatial chirp. And in the kxt domain, you can see the ultrafast lighthouse effect. And in the kx omega domain on the lower right, you can see the angular dispersion. And that's a pretty strong linear coupling. The shear, which is this red line that I've plotted over the top of the intensity profile, is extracted from the plots and fit to a polynomial to separate the first order or like largely correctable and the higher order contributions to the coupling. The temporal and spectral phase plots versus X can provide the arrival time delay and the frequency gradient, which is related to the pulse front tilt and the spatial chirp. So for a single shot, I took the temporal and spectral phase curves for several X positions, where now the rainbow is indicating this X position on the spatial profile. So here I have the spectral phase for these different X positions, and below I have the temporal phase for these X positions. And all that you should be seeing right now is just that the phase is changing as a function of position. But I'll remind you, just for anybody who might not be as familiar with the details of temporal and spectral phase, is that if you have a flat phase Gaussian in the time domain, you also have a flat phase Gaussian in the frequency domain. And if you have a linear temporal phase, for example, that produces a shift in the center frequency in the spectral domain, and vice versa. If you have a linear spectral phase, that produces a delay or an advance in the arrival time in the temporal domain. So a change in the slope of the linear temporal phase across X indicates that the center frequency is moving across X. So that is the analysis for a single shot. If you do this for all of the shots, you can get the arrival time delay and frequency gradient from the phase curves, and you can look at those systematic effects. So here, the purple is the arrival time delay, which is extracted from the spectral phase, and the red is the frequency gradient, the center frequency shift, which is extracted from the temporal phase plots below. So I did it for X and Y. So on the left, I'm moving across X, and on the right, I'm moving up the pulse. And the pulse's spatial profile. And you can see that these systematic effects, you can see the systematic arrival time delay and spatial chirp for both X and Y. The error envelope indicates the shot-to-shot fluctuations in that value. All of these shots were taken on the same day. And this basically corroborates the shear plots that I showed earlier, which were those black and white intensity integrated pictures, which were giving the pulse front tilt and the spatial chirp integrated over all shots. So these distortions also varied shot to shot. So this is the type of information that you can get from a single shot device, which is that the center frequency versus position is changing on every single shot. So here I've again mapped the spectral components to frequency or to wavelength here. And you can see that the red is clustering on the right and the blue is clustering on the left, but a lot of other stuff is going on. And you have these shot-to-shot distortions that are changing on every single shot. So for example, if you were to take like some method that scans the X position or the Y position, like say you're moving down in Y, the center of the laser pulse, you would get some value that might or might not be representative of the average value at that location, just from a single shot. So if you're integrating, and scanning over these values, you're going to miss this shot-to-shot fluctuation information, because your multi-shot methods have to typically assume shot-to-shot stability. So far we've seen the field at the striped fish measurement plane, but what about the focus? So because striped fish provides such complete information about the pulse, we can actually obtain the electric field at the focus as well through propagation. So you just use angular spectrum diffraction integrals to propagate the pulse in the z direction. You can choose any location you want. It doesn't have to be the focus. The focus is just interesting because it's used for many applications. So here I've taken the comet pulse and I've propagated it through the focus. And here's the movie at the focus. So again, the pulse is coming towards you. Out of the page, you've got your X transverse position, your Y transverse position, and the spectral components of the laser pulse have been mapped to RGB. And we're seeing basically you can see your pulse front tilt, you can see spatial chirp, you can see temporal chirp. So the spatial chirp is visible. You can kind of see the red in the bottom half of this pulse, but there is red coming in at the bottom, which is your temporal chirp, and your spatial chirp towards the middle of the pulse, and this sweeping motion is your pulse front tilt. Since the laser electric field is what creates and drives the plasma, the field at the focus can be used as input for simulation codes. Based on these measurements, we worked with JLF staff to correct the linear effects. So I called out that linear angular dispersion, and that was correctable by tuning the grading in the compressor. So the Comet laser is performing much better now. So that's basically my work that I did with the Comet laser. In my thesis, I also worked on simulating what would happen if we could measure different distortions on NIF arc. So the NIF's Advanced Radiographic Capability arc laser already has a great set of diagnostics: pulse width, shape, contrast, energy spectrum, temporally integrated wavefront, interbeam coherence, relative pulse delay in the near field and the far field. We have frog traces for 1 picosecond shots, but they are still missing a direct spatiotemporal wavefront measurement. ARC uses virtual beamline to model known spatiotemporal distortions of the laser. They've got a pulse duration map, integrated focal spot, this input profile for the preamp. So striped fish could be used to directly spatiotemporally characterize ARC with high resolution and validate the virtual beamline. Currently, they have spatial and temporal measurements taken separately. So here we have the time-integrated spatial profile and the spatially integrated temporal information. You could get the spatiotemporal information characterized by striped fish so I simulated some traces and results. It's possible that the arc field is spatiotemporally uncoupled, and we have EXYT is EXY times ET. But we know from VBL simulations that the spatiotemporal distortions probably exist on NIF-ARC. So this is a simulated strength of coupling for spatial chirp that is lower than the values that I observed at Comet, for instance. And this is that propagation plot through a focus. And so the question is, are there other distortions that we could be missing? Here I've plotted wavefront tilt dispersion, which produces a chromatic smear at the focus. Striped fish can identify and help to mitigate these distortions in the pulse. So that concludes the first section of my talk. The second section is on temporal structuring for optimization of laser-driven particle sources. So ultra-short temporal structuring may benefit laser-driven ion acceleration. In the most common scheme for ion acceleration, target normal sheath acceleration, you have this short pulsed petawatt laser irradiating a bulk target, and you produce beam-like accelerated ions from the rear surface. So temporal structuring of laser pulses can be achieved through laser spectral dispersion tuning. I've just written out the laser spectral phase in a Taylor series where phi1 is that linear phase that I was talking about earlier. And you also have phi2, your GDD, or group delay dispersion, or second order dispersion, and your phi3, your third order dispersion. So when you change phi2, you basically reduce the intensity a bunch, and you have these pulses that are much longer in time. And if you change the third order dispersion, you get a more subtle effect where the pulse leans, and you get like a pre-pulse or a post-pulse. And you can also change both phi2 and phi3 to generate more exotic temporal pulse shapes. The takeaway here is that we can both accurately manipulate and measure the temporal pulse shape. We ran an experiment at the ALEF laser at CSU through LaserNet to explore temporal pulse shaping for ion acceleration. So we have a pulse coming in from the right at 800 nanometers and focusing onto a thin foil target. We used a proton diagnostic called ProBees, which is the proton beam imager and energy spectrometer. We also ran an E-spec and a Baxter for the X-ray spectrometer. So experimental validation of pulse shape control at CSU was completed using frog traces with 3 femtosecond resolution. So on the left, I have a frog data trace for a pulse with negative third order dispersion and 0 group delay dispersion. And on the right, I have a pulse with positive GDD and TOD, which is like the most complex pulse that we generated. So the frog data trace and retrieve trace match well. So this is the simulated pulse shape, and this is the measured pulse shape where the error bars just indicate the shot-to-shot fluctuations. And you can see that the reconstructed trace and the bin trace match pretty well. So frog measures the intensity, temporal intensity in phase, the spectral intensity in phase, is also used to provide the spectral phase measurement for striped fish for the reference pulse. And ProBees provides simultaneous spatial and energy resolution of the proton beam at a high repetition rate. So ProBees, the proton beam imager and energy spectrometer, is this rep-rated diagnostic for proton beams. So here we have this city block. So that's you're increasing the wedge thickness on your filter, and you're basically just repeating this like city block pattern across the entire spatial profile of the proton beam, which gives you energy discrimination for the proton beam. Then you have a scintillator behind that mask, and which converts it into a light signal, which you can then image onto your camera. So ProBees can be used at a high repetition rate. The advantage is that you don't have to deal with RCF stacks to operate, so you replace your films with a digital detector, and that also really improves the analysis speed. So the high rep rated ProBees setup enables rapid analysis. Here we have the Probe's mask that we used at this experiment, the raw data corresponding to this mask, and the grid registration for a different shot based on the image registration to this shot. So you don't have to deal with image registration problems that you might have to deal with, because you're basically just leaving the camera in place and taking a ton of data so you can analyze it much more rapidly. So what we saw was that spectral dispersion appears to be a strong tuning knob on proton dose. Here I'm showing again the laser spectral phase Taylor series and reminding you of the pulse shapes. So this green box is your negative GDD, which has these sorts of pulse shapes with bumps in the temporal profile. The positive GDD is basically the reflection of that, so you're getting these different shapes by changing the third order dispersion. And then the center box, the red box, that's your third order dispersion, negative, 0, and positive third order dispersion. So what you can see is this is just the dose in pixels for the 3.9 MeV channel of the Probe's on a 7-joule laser energy scan. So we scanned pulse duration, we scanned all of these different pulse shapes, and the highest dose was obtained when the third order dispersion was positive, which creates a post pulse. This pattern was also seen not just in the 3.9 MeV channel for proton energy, but also in the 5.8 and 7.3 MeV channels, so this result shows a promising dispersion tuning effect, especially with third order dispersion. We took 48 spectral shaping shots. As I said, these are from the 7-joule energy scan. And the third order spectral phase improved proton dose when the second order spectral phase was close to 0. This pattern persisted up through 7.3 MeV, which was when the proton dose dropped off. Future work involves recently completed beam time to further explore this relationship between the spectral phase and proton dose. Another LaserNet time was recently completed in December to further explore this work and expand the laser parameter scan. We're also hoping to do ensemble simulations for full interpretation of results, comparison to other diagnostic, calibration of the Probe's diagnostic, and we hope to use the Probe's analysis in a feedback loop to enable transfer learning. So the third section of my talk is on spatiotemporal structuring of laser intensity and phase to generate optical vortices. Optical vortices can maybe benefit TNSA by providing a tailored electron sheath for ion acceleration. Ion and electron acceleration processes can benefit from advances in laser technology. So on the left, I have TNSA with a Gaussian pulse to compare to TNSA with a donut laser pulse. And the question is, how can we use structure light to tailor our particle acceleration? These preliminary simulations compare proton distribution over time for Gaussian and donut modes. Basically, the only thing that we can say from these plots is that the proton distribution is different in the Gaussian mode and in the donut mode. And we're curious to see what actually happens in experiment. An optical vortex is basically just this. Instead of having just a Gaussian spot and a flat phase, you can create this donut shape using this spatial phase that increases from 0 to 2 pi, and that produces this spiral wavefront. So in this work, they found that the simulated intensity and measured intensity for the 0 and first order optical vortex matched pretty well. So these are our off-axis spiral phase mirrors, which we are now making in collaboration with the MRF at Livermore, show promise for generating high-intensity optical vortices, but have to be validated, since the key component of this optical vortex is this rotating wavefront. So you have to measure this spatial phase. Current validation methods have been limited to spatial and temporal measurements taken separately, so your space average temporal and your time average spatial. But the defining feature is the spatial phase, which would be measured on-shot with striped fish. So striped fish can be used to provide the first high-intensity measurement of the spatiotemporal phase that defines the optical vortex. Without spatiotemporal validation, we won't know whether we're generating a simple optical vortex or a spatiotemporally perturbed beam that doesn't have that characteristic ring shape at the focus. So here I'm just plotting the propagation behavior for an optical vortex, and here I'm plotting the propagation behavior for a spatially temporally distorted optical vortex. So this work is ongoing with a recent LaserNet proposal awarded for Bella. I built a striped fish for Bella when I was a grad student. It's currently in place, retrieving the spatiotemporal distortions on shot. As this is a raw striped fish trace from the Bella laser. This is the 100 terawatt system. The experiment is currently scheduled for May 2023, and these are just some simulations of the simulated and retrieved intensity and phase of an optical vortex. So in summary, this talk discussed laser metrology for precision-controlled secondary sources, beginning from high-intensity on-shot laser electric field measurements, which included on-shot measurements of the comet wavefront and an application to NIF-ARC, moving into temporal structuring for optimization of laser-driven particle sources, where I showed some recent work that found that laser dispersion tuning is a strong knob on proton acceleration, and ending with spatiotemporal structuring of laser intensity and phase to generate optical vortices, and my current work, which investigates the use of these vortices for particle acceleration. The proposed work for the HEDS Center Fellowship basically answers the question, how can we take these methods for spatiotemporal pulse characterization and apply them to study the physics on target? And can we apply wavelength-multiplexed holography to directly characterize laser plasmas in space and time? So that's all I've got. Thank you.
Thank you very much. That was a great talk. Are there any questions? And if you're joining us online, feel free to put your questions in the chat field and I will read them.
You
Yes.
said that you've looked at these different shape pulses for the TNSA proton acceleration. You've actually looked what the protons themselves look like after. I mean, obviously you've done it with the tuning the wavefronts, but when you go to like the donuts and things.
No, that's the work in May at Bella that's coming up. Yeah. Yeah.
So I had a question.
Yeah.
So while you were doing your first section, I thought it was really cool, like all the diagnostics you were showing. And so my next question was going to be like, how do you use, we usually think of all those imperfections in the wavefront as a bad thing, but then like, how could you use them for good and try to get positive things? And so your next stage of your talk then was essentially answering my question of, but I was curious if you could explain that a little more of like exactly what changes bring about getting better proton beams.
Well, a paper that I recently wrote was talking about using pulse front tilt to direct proton beams. And we found that it was just a simulations paper that I did with Blagoya. But basically, we found that you can get a different direction to your proton beam depending on the pulse front tilt of the incident laser pulse, or of the electron beam depending on the incident laser pulse, which might be interesting to direct those to direct those electrons. Basically, could have many applications. Maybe if you want to use it as for a secondary target or something like that to irradiate that target. So there are lots of different things you can do. I'm also interested in seeing what we can do with OAM for wake field. So there are lots and lots of potential applications that you can have. I mean, lots of spatiotemporal distortions are deliberately induced, like in chirped pulse amplification, you deliberately induce angular dispersion in order to get, that amplification effect. So yeah, these distortions are basically commonly introduced and used all the time in the lab.
Thank you. So we do have a question online from Peter Sellier, who says, this is an exciting new capability. Are interpulse polarization variations of concern? Would they affect the experiments? Can they be measured or manipulated?
Intrapulse, well, this work is just talking about one laser pulse. I guess the question is about, like, say you had two beams and you had some polarization rotation in one of the beams, would you still be able to characterize it?
Can they be?
Yeah, hi, this is Peter. Yeah, I guess
I'm
the question.
not sure. I could.
Can you hear me?
Yes.
So the question is, you can measure in great detail these wavefront distortions, but the it suggests to me there may also be polarization rotations that are occurring, and it's not clear to me that the measurement can extract that information. So that's
No.
one thing. The other thing is, let's say they were present in the pulse. I presume they may have some effect on the experiments in particular cases. And so then that leads to the third question I asked is there a prospect for measuring polarization variation inside the pulse, possibly using polarization sensitive elements in your setup, and probably have to make it more elaborate? Has any thought gone into any of that?
So, yeah, you're right. Currently, striped fish doesn't measure polarization. You could measure polarization, as you suggest, by introducing polarization-sensitive components to a setup. That's something that I proposed to do at Bella and was hoping to get done over there, but we basically ran out of time. I am interested in adding that polarization measurement to striped fish. It's something that I would be very interested in doing, but it is something that has not yet been done. I would like to add it onto the setup at Bella.
Thanks.
Thank you. So there's also a question from Mingsheng Wei. It says, great talk. You said positive GDD resulted in higher dose of protons. What's the physics behind it?
So Blagoya did a set of simulations that kind of got at this. So yeah, at around 0 GDD, we noticed that a post pulse was improving the proton dose at 3.9, 5.8, and 7.3 MeV. I think that what his simulations seemed to show was that the protons basically got a little extra kick from the post pulse. But that is basically that's basically my understanding of his work. My role was basically just to compare these two measurements, but I think that the simulation work to explain the effect is kind of still ongoing.
Just one
Another question from the audience.
So the way I understand a striped fish is that you're spectrally dispersing the pulse into all these different colors on your camera. So how many each of those colors represents like your resolution in time as well, right? So
really
typically how many points is necessary, right? I guess because
yeah.
Yeah,
I mean, it depends if you have like if your spectrum is modulating like really quickly, there is like a point at which you wouldn't see like super rapid modulations just related to like the Nyquist sampling of the spectrum, like if you had really rapid oscillations. So you can get around 81 spectral points typically, which gives you, so for example, like if you have a relatively Gaussian spectrum, like that would be like more than enough to sample it. But if there are any like tiny wiggles in the spectrum, you might not see those.
so experimentally you're showing, I think it's like 25.
Yeah.
I think, right?
Yeah, I chose different array sizes for different simulations.
But even your raw data though, right? I think.
Oh yeah, so that was like at the comet, well, I won't bother, it will be a long way to go back, but yeah, so for that array, I think I had like I ended up with like a 3x5 array.
What does that correspond to time resolution?
The temporal resolution, let me see, was something like on the order of picoseconds, of 0.1 picoseconds, I think. Yeah, I think it was about 0.1 picoseconds.
Okay, so if you wanted to use this on like a femtosecond laser pulse.
Which is what it's typically used on. So this was an extension of it to measure longer pulses.
But you have, yeah, I guess would you need more spots on the femtosecond then, like to get the resolution down?
Yeah, so you would want to get the best temporal resolution, you would want as many spots as you can get, but then you also have a trade-off with the spatial resolution because you're fitting it all onto one camera sensor. So it's
Right.
kind of like a trade-off that you have to calculate for each laser pulse. How good of a temporal resolution and how much spatial resolution do you think is required?
Okay. And I guess if you had a monochromatic pulse, then you just get one spot, but you can retrieve from that single spot, you can retrieve the entire spatial phase. So, right, just from the
Yeah.
interference pattern. So, because I noticed at the beginning, you used the word astigmatism, and it felt like I always think of astigmatism as a spatial phase aberration, but is it also something that you use the word to describe a chromatic aberration too? So if I have a flat phase, but my colors are bent up in like a cylinder on the lens, but as the phase is flat, is that still an astigmatism, or was that called it's something different?
Yeah, when I was talking about astigmatism, I was talking about how like the pulse came to a focus in Y before it came to a focus in X in that
So
propagation
that's
plot.
spatial then. Well, I
Yeah.
guess I don't know how a chromatic astigmatism would change
Yeah.
how focus is, but
You
I
can.
assume that there's because you think in space you use Zernike polynomials to describe your spatial phase, but I guess you could do the same thing with the colors too, right? You have a change in your colors across the lens, and you could use the same basis set to describe that. So I just don't know what it would look like on a focus. So
Yeah.
Thank you. Are there any more questions? Yeah, I don't see any more online. So if not,
Yeah. Sorry,
first
may I
off,
have one more? This is Klaus. Can you
please
hear me?
give Liz a warm welcome if you see her in the hallways. Her office is in building 481 on the 2200 wing. And otherwise, let's give her a warm thank you for her great talk. Hope to see everybody here next time. And otherwise, have a great rest of your day. Bye-bye.